Okay, so we've been doing all this oscillator stuff. I've been doing all this oscillator stuff, and it's all in a playlist. The playlist is down below. I think that you can find it. I don't know how to put all the little links up there and stuff like that, but and I derived the damp driven oscillator. That was the last thing I did. But now let's just play with the damp driven oscillator. And so I think we need to do a little bit of a review. So here's this is really quick. I have this really complicated problem. I put all the details in the previous video. So, but I want to play with the damp driven oscillator now. So here we have a mass on a spring. There's some restoring spring force that pulls it back to the origin. I'm calling the origin x equals 0 so that the stretch is x. And then we have a damped force. So this force depends on the velocity of the mass, and it's in the opposite direction of the velocity. It's like it's moving through oil or something. And then we have a driving force. So there's some other oscillating force that's just pushing it back and forth that we can change both the amplitude and the frequency of, and that's the damp-driven oscillator. So how do we solve it? Well, it's not really that. It's not simple, okay? But let's start with Newton's second law. This is your flash bang super fast version of it. So I have those three forces. I have the spring force, I have the drag force, I have the spring force negative kx, the spring force negative bx dot. So here I'm using dot notation. So x dot is the derivative of x with respect to time. X double dot is the second derivative. So I have spring force, drag force, and the driving force f of t, and that's going to be equal to mass times acceleration, which I call x double dot. Now, it's going to help if I write the acceleration force, so which is the driving force divided by the mass. Because if I divide all the sides by the mass, then I can get it into this nice form like this. Okay, so here's x double dot 2 beta x. So beta is a parameter based on the drag and the mass, and the 2 is there for reasons. There is a reason that there's a 2 there. Omega naught is the simple harmonic oscillation frequency. It's square root of k over m. And there you go. So that's the equation that we want to solve. That's the differential equation we want to solve. It turns out that the solution to this can be broken into a characteristic solution, xc of t, plus a particular solution, xp of t. And the characteristic solution is the solution to this when the driving force is 0. And that we know the solution to. So this is the solution to that characteristic. This is the characteristic solution, and it looks like this. This is the solution to the damped oscillator. Yes, I do have a video explaining this, and it's part of that playlist down below. So this one's not too terribly difficult to derive, but there's some stuff. So let me just point out some important things here. This e to the negative beta t, so that's that beta parameter. Well, I'm going to show you this in a second. Yeah, I am. Never mind. And then omega 1 is this term. Okay, so in order to get it into a cosine function, omega 1 is the difference between omega squared. That should be omega 0 squared. I did that same mistake before, didn't I? That's omega 0 squared. Well, I have it better later on. Okay. So that's our solution. And what does it look like? Well, it looks like this. So here's the generic solution. What is the solution in exponential form with the complex exponential? So C1 and C2 could be complex. But the point is that this is the case where beta is less than omega. And so you have actually two functions together. You have this e to the I omega 1t plus e to the negative I omega 1t. That's an oscillating function that looks right there. Then you have this exponential decay function, the e to the negative beta t. And then you combine those together and you get that's a damped harmonic oscillator. But the point is that that's the characteristic solution to the driven harmonic oscillator. So that's important. Then we can get, it's not trivial. You got to assume the driving force is an oscillating term like e to the I omega t or something like that. And you can get this. And there's a lot here. Okay, I'm skipping over some stuff. But this is the solution to the damped driven simple harmonic oscillator. Let me go over some of the points. So AC is a parameter based on the initial conditions. So Where did you where'd you let it go at time t equals 0? What was the velocity at time t equals 0? Phi is a constant also depending on the initial condition. So you have two initial conditions, right? I need to know the position and the velocity at the start, and I can find those. Neither of those are position or velocity, okay, at time t equals 0. You can find them. And I do in another video. Okay. Then we have F0. This is the driving amplitude. So the driving force is a sinusoidal or an oscillating function, and this is the amplitude of that function. So it's the amplitude of the force divided by the mass, because we're dealing with accelerations here. Omega, this omega, there's three omegas. There's omega 0, which is square root of k over m. There's omega, plain omega, and that's the driving frequency, so how fast that thing moves back and forth. And then so there's our omega naught, and then beta is our parameter based on the drag coefficient, b over 2m. There's a reason 2's there. Okay. And then omega 1, I did it again. It should be omega 0. It should be omega 0. Yeah, it should be omega 0. Yeah, it should be omega 0 squared minus beta squared. I did it again. Okay. And then we also, if you'll notice in this solution, we have this gamma term in there, and that's really just to make things simpler. So gamma is just 2 omega beta. It turns out that it's easier to do that. We don't have to do that way. Some people will leave as 2 omega beta. So that's that driving frequency, and that's a dampening term. And then we have this theta term. It's another phase parameter. It also depends on a lot of things, so we don't really put it in there. We just write it as theta. It depends on gamma, which is right there, and it depends on omega minus omega naught, omega squared minus omega naught squared. So it depends on the driving frequency and the spring constant and the mass, and it depends on everything, because beta's in there too. Okay, so let's look at the solution in a little bit more detail. Here's that same solution. So this is important. This term, as t gets larger and larger, this part right here goes to 0, right? So this whole term eventually dies out. So the long-term solution, you don't even have to worry about that. Then we have over here, this term, it's a cosine term. So it just goes between -1 and 1. That's all it does. It just oscillates. Yes, theta does depend on all these parameters, but once you have those, it just oscillates. So we get an oscillating term. And then we have this other term, which is just the amplitude. The amplitude of the oscillating term. And it depends on the driving amplitude. It depends on the fundamental frequency, omega 0. It depends on the driving frequency, and it depends on gamma, and gamma depends on both the driving frequency and beta. So it's all in there. The amplitude depends on all that stuff. And just as a reminder, that's what I just said. Theta is there. Gamma is there. Okay, so let's see what happens. Now, I skipped over phase space. We're going to make a phase space plot, and I've made a video on this before. I'm not going to go over it, but really, we're plotting position versus velocity, and that way we can kind of see the motion of the whole thing. So what happens if I start with omega equals 0 and I increase it? What would happen to my phase space plot? It looks like this. So as you can see that as I should pause it. It's actually pretty good animation, but you did notice that the amplitude of oscillation, the phase space it took up got really big at one point and then decreased. So this is going from omega driving frequency of 0, which would just be a damped harmonic oscillator, and to some magic point where it got really big, and then back here it kind of dies down into this. I kind of have a large driving frequency, but as the frequency gets really high, then it just gets kind of weird. Imagine that if I had one end, a mass on a spring, and I'm shaking this back super fast, the mass isn't really even going to do anything. Okay. Let's play that one more time. Actually, I can scroll. So right here, it's very low frequency. It looks like, and I cut off part of it just so you could see it. It starts over here and it spirals in. That's just a damped harmonic oscillator. But then over here, you'll notice that the amplitude, the amplitude of oscillation, which is the space this way, and the amplitude of velocity, which is that way, gets really big. But it doesn't stay big. As I increase the frequency, it gets smaller again. Okay, so that's cool. Okay, so let's look at just that amplitude part. So again, this term right here decays out, so we don't have to worry about that. So let's call this amplitude just A. I'm just going to call that A. That's all I'm going to do. And omega 0 is that, and omega is the driving frequency, and that's the gamma. And so the question is, and there's beta. So if you just look at this term, what's going to happen as omega goes to infinity? Well, as omega goes to infinity, this term is going to get really, really large, and it's going to be bigger than omega 0, but that's fine because it's squared. So this term is going to get really big. Gamma depends on omega too, right? So that's going to get big. So this whole thing on the bottom is going to get big. And as this thing gets really, really big, what happens to the amplitude? It gets smaller. Okay. What if beta is equal to 0? What if there's no drag? If there's no drag, well, let's just see. What would change in here? Well, that doesn't depend on drag. Does that depend on drag? No. Does omega depend on drag? No. It only depends on this term right here. So we'll still get a particular frequency with the largest amplitude, just like we did before, even without drag. Okay. So let's make a plot of the amplitude as a function of the driving frequency. It's pretty easy to do. I did this in Python. So here's that term. So at low frequencies, the amplitude is very, very low. This is a long term, right? Because that we cut out that transient term from the beginning. So we have that. And then you'll see up here that it peaks at some point and then it dies down again, which is what we said. Now, this peak would be when this term on the bottom is the smallest. Well, gamma can't be 0, right? So that it's not going to be 0. And this term can be 0 when omega 0 is equal to omega, when omega is equal to omega 0. And actually, you look right here, 10, I actually have omega 0 of 10. So that's my resonance peak right there. Okay, but what if you change beta? What if I make beta smaller? Well, that's going to change this term right here. If this term gets smaller, because beta is going to get smaller, then I'm going to get a larger amplitude. And there's this is beta is equal to 1 right here. Here's beta equals 0.5. What if I make beta bigger? That's beta equals 2. Not only does the amplitude get lower, but it spreads out more. Okay, so there's actually a really cool application here that's related to this. It looks like this. This is a simulation in FET. If you're not familiar with FET, you should be familiar with FET. It's pretty cool. So here I have a variable voltage supply. There I have a resistor, a capacitor, and an inductor. And I can change the frequency, and I can plot the voltage across there. And you can see that at certain frequencies, I get a higher amplitude voltage across the resistor, and some I get lower. It's the same problem. So here's the circuit with variable voltage, resistor, capacitor, inductor. And so Kirchhoff's loop rule says that the change in voltage around the loop is 0. So I can write that as the driving voltage minus the voltage across the capacitor, resistor, and inductor. Well, the voltage across the inductor, it depends on the rate of change of the current. So it's L di dt. The voltage across a resistor is I times R, and then the voltage across the capacitor is Q over C. But I is the derivative of Q with respect to time. So I can actually write these all in terms of Q. So this would be a derivative with respect to time of Q, and that'd be a second derivative. So, and if I write Q double dot as second derivative of Q with time, Q dot first derivative, you kind of see what this looks like, right? It looks just like a damp-driven harmonic oscillator. So I have a velocity-dependent term, a second derivative term, and a constant term. It's the same thing. Okay, so let's try a demo. It didn't really work out perfect, but here is a demo. What I wanted to do was to show you that what happens if I have two masses of different masses on a spring, and I move the pivot point up at the same time. And you should be able to get one of them to oscillate and resonate much more than the other one, depending on how you oscillate that. It's kind of a cool trick. There's another version of this where I have stuff on and I should make that video. It was masses hanging from different lengths on a string, and you can just swing it back and forth and get one of them to swing bigger and bigger and then not the others. It's the same idea of resonance, that the resonance depends on the natural frequency of the thing. And there you can see my face close up, and I should go back because I don't want to see that. And that is where I will end. I think that's it for my oscillation video. I think I did as much as I wanted to do. I might add some stuff to this later, but if you have questions, ask me later, comments, and that's that. I'll talk to you later.